Hello everyone, I am Thatcher, and today I will be showing you an elegant visual representation and shift in perspective of a potential solution to solving the problem of Tetra Slice, which can be found on nrich.maths.org. The problem goes like this. ABCD is a tetrahedron. Points P, Q, R, and S are the midpoints of sides AB, BD, CD, and AC. Prove that PQRS is a parallelogram. In the Getting Started section of the problem, it proposes that we should consider expressing the points and sides as vectors. However, I will not be using vectors in this video, instead using basic geometry and 3D modeling, thanks to GeoGebra, to explain my solution. As you can see, I have created a replica of the tetrahedron in Tetra Slice with point A, B, C, and D, and points P, Q, R, and S are the midpoints of AB, BD, CD, and AC respectively. How do we go about proving it? Well, let's first fix the points B and C in place and allow only D to move. We can then look at a 2D representation of one side of the tetrahedron. Now, let us focus on the left half of the triangle BCD as we move point D along the horizontal axis. As you can see, there is always a parallelogram made by points S, R, D, and the intersection point of lines AD and PS, which we'll call V. There are also two triangles that are apparent, triangle SCR and ASV. Both these triangles have the same perimeter and area due to the fact that S is the midpoint of AC, R is the midpoint of CD, and V is the midpoint of AD. Thus, by adding these two together, we form the equivalent parallelogram SRDT. Now, on the right half of the triangle, we have triangles ATP and PQB, as well as parallelogram PQDT. Again, we observe the same equality of area shown previously. The triangles ATP and PQB add up to form PQDT, and by adding together the parallelograms SRDT and PQDT, we get the original parallelogram proposed in the problem PQRS, represented in 2D. But most importantly, notice that the lines SR and PR are always parallel to AD, hence parallel to each other. Then, let us move on to the top view of the tetrahedron. Again, with B and C fixed in place and only allowing D to move. By sliding D across the horizontal axis, we again see two triangles form on each section of the triangle BCD. For triangle ACD, we have two smaller triangles, CSR and RDU, where U is the point of intersection of AD and QR. Adding them together, we get the parallelogram AURS. Again, this is true for the right section of the triangle, with two smaller triangles forming the parallelogram, hence preserving the equality of area. And just like last time, notice that the lines SR and PQ are always parallel to AD, hence parallel to each other. Let us now move on to the final 2D representation of the tetrahedron. Now, we have two triangles, the larger one ABD and the smaller one PBQ. Notice that these two triangles are similar. This is again due to the fact that P and Q are the midpoints of AB and BD respectively. We then move D along the horizontal axis. Again, we observe the proportionality of the ratio between the sides of the smaller triangle and the larger triangle. Another neat trick we could do is by moving triangle PBQ up here. Notice how it forms a parallelogram? Well, just like before, by adding these two triangles together, we form the parallelogram in the middle. Notice, for the last time, that lines AD and PQ are parallel to each other, with PQ overlapping exactly with SR. Right, let us finally go back to the 3D representation. As we have observed in 3 2D representations, by fixing 2 points and moving one, the respective lines are always parallel to each other due to the fact that many of their respective points are midpoints of corresponding lines, and that the equality of areas of smaller shapes that the lines form is preserved. And this is true for all tetrahedrons, regardless of what points you choose to move. Just to be clear, I'm not proposing this to be actual proof, but what I am trying to portray is a simple yet elegant perspective to a potential solution to the problem without using vectors and position vectors or other possibly more advanced mathematics, but using only simple geometry and observations. That is the beauty of mathematics. There will always be more ways than one to solve a problem, and a shift in perspective can change a seemingly difficult problem into a simple, elegant one. Thanks for watching.